Hey, this is Mr. Aiden. We are finishing up Chapter 6, Additional Topics in Trigonometry. We will be out of trig after this section, which is the dot product of two vectors, which is section 6.4. Now, if you remember back to elementary school, in elementary school, you did like 3 times 4 or 2 times 3, and your teacher would put a little x in between, and then they moved to a dot. And you went, what happened to our x? And they gave you kind of the interesting dynamic of saying, well, you're going to use x later on. Okay, now what was right? Was it using the dot or was it using the x? Well, today we're going to talk about what's called the dot product. And the dot product is we have two vectors here. We have vector u, which has an x and y component. We have a vector v, which has an x and y component. And u dot v is equal to the x components multiplied plus the y components multiplied. Now, back in elementary school, when your teacher did 2 times 3, well, should they have been doing 2 dot 3 instead? Well, let's take a look. Let's say we have a vector 2 and a vector 3. Okay, now what is this vector 2? Let's call that u, and vector u has 2 in the x and nothing in the y. Vector v has 3 in the x and nothing in the y, which means what were they really doing when they multiplied? They were really doing u dot v, weren't they? They were doing 2 times 3 is 6, plus 0 times 0 is 0, which end up giving you 6. They should not have been doing the x. They should have been doing the dot all along. Because what's happening here is we were really just taking a look at the vectors in the x direction when they did 2 times 3. They were not looking at any y direction here. Now, if there's a y direction in the component, it actually adds into that value. Now, I hope you can see there's only one value you get, which you're not getting an x and a y component, which means your answer is scalar. What do we mean by scalar is it only has magnitude only. There's no direction. There's no x and y component. It is just a number, a magnitude, a how big is this value. And I hope you can see is the x's are relating to each other and the y's are relating to each other. So if we do some examples here, we have one vector, and we call that vector u. We call that vector v. So u dot v is going to be my 4 times 2 is 8, and I'll do that. 4 times 2 is 8, plus 5 times 3 is 15. So we have 8 plus 15, which ends up giving you 23. Again, a scalar quantity here. Now let's take a look at this next one. This next one we have our 2 times 1 plus negative 1 times 2, which gives you 2, plus negative 2, which gives you 0. So in this case, we got 0 for these two values. Okay, and last we have 0 times 4 plus 3 times negative 2, which gives you 0 plus negative 6, gives you negative 6. I hope you can see in every single one of these dot products, we're left with just one value, a magnitude, a scalar quantity. Okay, now I want to really take a look at this middle one right here. This middle one, and I really haven't told you exactly what a dot product is. A dot product is how two vectors or more vectors are relating in terms of their x's and the y's. What do they have in common with one another? What do they have in common with one another? You can see we're looking at how the x components are in common with one another, and the y components are in common with one another. If we take a look at this b value here, this b, you can see I'm going to do a little bit of a pretty bad xy plane here. You can see the first vector is 2, negative 1. So 2, negative 1. So my vector is right here. I'm going to call that vector u. Okay. And then right here is 1 positive 2, 1 positive 2 right here. So that is this vector right there. Do you see how much does the x values and the y values end up in common with one another is nothing. Nothing. We get 0. They don't have anything in common with one another, which means these two vectors are perpendicular to each other. Perpendicular, which we are going to call a more technical term is orthogonal. Now, if I say orthogonal, you think perpendicular. If I say perpendicular, you think orthogonal. They are orthogonal with one another. They have nothing in common, and that's why my dot product was nothing. That's why when you have 0 times 0.4, your answer is always 0, isn't it? Because you have nothing in common with one another. And so that is called the dot product. Now we also have a bunch of properties of dot products. You can see down here. In this one we have u dot v. So I'm going to take u dot v. So I take u dot v. I take -1 times 2 plus 3 times -4. I still have vector w on the outside, which is 1, -2. So I'm going to do the dot product of the inside. I get -2 plus -12. I have this w on the outside. So we get -14. And now we're going to, this is like your multiple. We end up getting -14, positive 28 right there. And you can see how when we had a scalar multiple, we end up getting a vector quantity at the end. Let's take a look at B. B, we have u, which is -1, 3. We have dot 2 times v, which, what do we do when we have a scalar multiple? We double it, everything, right? 4, -8. Now we can do the dot product. So we end up getting -1 times 4, it's -4. Plus 3 times -8, that's -24, sorry. And that gives us -28. We had a dot product, so what do we have? We have a scalar quantity at the end, -28. And then last but not least, we have the magnitude of u, okay, which we know how to find the magnitude of u. We can do the square root of -1 squared plus 3 squared. So that's 9 and 1, that's 10, that's the square root of 10. Okay. There's another value though, is if we're trying to find the magnitude of u, it's the square root of u dot u. Everything they have in common with one another. So how do we find u? U is the square root of -1 times 1, that's 1, plus 3 times 3, that's 9, and we still get square root of 10. You can see how that property is the same as your magnitude. Okay. Now, if we want to find the angle in between, we have this beautiful formula right here. Is we have two vectors. We want to find the angle in between. Let's say it's not even a 90-degree angle. We're going to use this cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v. Okay, so let me write that down for us. Cosine of theta equals u dot v over the magnitude of u times the magnitude of v. So that means we got to find all these things, don't we? Okay, we need to find u dot v. U dot v. So how do we find u dot v? We do 4 times 3 is 12, plus 3 times 5 is 15. What do we end up getting is 27. So that's u dot v is 27. That goes on to my numerator. My denominator, we're going to do the magnitude of u. How do we find the magnitude of u? Is we do the Pythagorean theorem. 4 squared and 3 squared square root. We end up getting 5. That's a 3, 4, 5 triangle. The magnitude of v ends up being 3 squared, which is 9, and 5 squared, which is 25, which gives me the root 34. Root 34. So what do we have on our denominator is 5 root 34, because that is u times v, okay, the magnitudes. Okay, so now we have cosine of theta equals 27. I'm going to make sure I do this on my calculator. 27 divided by, make sure you put in parentheses, 5 root 34. And we get 0.9261. How do we find our theta? Is we do arc cosine of that answer, cosine to the -1, and we get 22.17 degrees, and that is my angle. If we end up getting 0, okay, if we end up getting 0 for these values on the numerator and denominator, cosine of 0, it ends up giving me 90 degrees. They end up becoming orthogonal with each other, and we've talked about that orthogonal. They have nothing in common with one another. Okay, just like a lot of the guys and the girls in the class. Okay, so the nothing in common. So here we have u dot v. Okay, so we have 2 times 6 is 12, plus negative 3 times 4 is negative 12. That ends up being 0. So cosine of theta equals u dot v over the magnitude of u times the magnitude of v. 0 over anything. Who cares what the magnitudes are? We end up giving us 90 degrees, or orthogonal. Okay, orthogonal. Now, the only hard part of this chapter is a thing called projections of u onto v. Okay, so let's say we have this vector u here. Can you see this vector u is made up of 2 components? It's made up of a component in the x and a component in the y. We call this component in the x w1, and we call this component in the y w2. Okay. Now we have this vector v right here. We have this, I'll put that in a different color, this vector v right here. Now this vector v is smaller than w1. So you can see how this vector v is some scalar multiple of w1. So I know w1 is equal to some k, some value times v, isn't it? Okay. It might be double, it might be less, it might be a bunch of different things. What do I also know is I also know w1 and w2. If you add them tail to tip, it equals vector u. Vector u. Okay? And so what do I have here is I have a projection. Is u dot v, and I'll kind of walk us through this, is u dot v equals my kv plus my w2 times my vector v. Okay, that is the dot product on each side, which means that we have, according to my properties, we have our kv dot v plus our w2 times v. And what do we know? This kv dot v, this is really some constant times the magnitude of v squared plus 0. Why is w2 and v 0? Because w2 and v are orthogonal to one another. They have nothing in common, which means that this is equal to k, the magnitude of v, squared. Okay? And I hope you can see is this value right here, if this is equal to u dot v all along, we can see that if I divide this, that equals this k right here. And that equals this equation down here, which we call the projection of u onto v. The projection of u onto v is u dot v, what we have here, divided by the magnitude squared times your vector v. Let me give you an example of this. So we have our 2 vectors here. We have vector u, which is 3, negative 5. So 3, negative 5 is right here. And I'm going to draw that vector. That's vector u. Okay. That's pretty good. That's not bad. I'm going to call that vector u. And we have vector v, which is 6, 2, right here. I wish I was 6, 2, but I'm not. Here's vector v. Okay, we'll call that vector v right there. So we have vector u and vector v. It says write u as the sum of your 2 orthogonal vectors, one of which is the projection of u onto v. Projection of u onto v. And so w1 equals the projection of u onto v. And according to my equation right there, let's take a look at my equation. I have u dot v, so u dot v over the magnitude of v squared times the vector v. Okay, so let's take a look at each one of these things. Let's first do u dot v. U dot v. I have 3 times 6, that's 18, plus negative 5 times 2, that's negative 10. That ends up becoming 8. So what do we have? W1 is equal to 8 on my numerator. We're going to do the magnitude of v. What's the magnitude of v? Is equal to the square root of 6 squared, that's 36, plus 2 squared, that's 4. That ends up being root 40, which means the magnitude of v squared ends up becoming just 40. So we're going to have 40 right there. Okay. Now what do I know vector v is? Vector v is 6, 2. Again, I'm just following the formula to find the projection of u onto v. Okay. So this ends up becoming 1/5, right? 1/5 of the vector 6, 2, which ends up becoming 6/5, 2/5. And those are my components of these two vectors. Okay. Now, what do I also know is it says write u as the sum of two orthogonal vectors. Two orthogonal vectors. Now, what does that mean? How are we doing this projection? This u is made up of two vectors, which we're going to call w1 right here and w2. Okay, so w1 and w2 ends up becoming vector u there. Vector u. Which means w2 is equal to vector u minus w1. Okay? Vector u, we know what vector u is. It's 3, negative 5 minus w1. I just found what w1 was. w1 was the projection of u onto v. So w1 was 6/5 and 2/5 in the x and the y. Again, I got to get some common denominators here, don't I? I got to get some common denominators. So I end up getting 15/5, that's 3, and negative 25/5, that's at negative 5, minus 6/5, 2/5, which means W2, and I'm going to write this over here, W2 is 15/5 minus 6/5, that ends up becoming 9/5, and negative 25 minus 2, that's negative 27/5, and that is what we call W2 right there. W2. And so you can see that is my W2 is 9/5 and negative 27/5, and you can see, hopefully you can see, if I take W1, which is right here, that's 6/5 and 2/5, and I add it to W2 right there, I end up getting vector v. If I take this, again, I take this vector w, and I add it to this vector w2, w1 and w2, that ends up becoming vector v. That would end up becoming 3/5, because w1 and w2 ends up becoming this vector, sorry, not vector v, vector u, because these two vectors are added up on one another. And so that is ultimately all of additional topics in trigonometry. That's the dot product of two vectors. Chapter 6.4, we are done with trigonometry. So have a little party, enjoy it, and you can take those degrees and radians and put them to bed for a little bit. Take care, guys. I'll see you in class.